Hello, everyone. Welcome to my talk. Sorry, I cannot be in a conference room. I hope the quality of the video is good enough. My name is Jianfei. I'm from Bloomberg PRA engineering team. PRA stands for Portfolio and Risk Analytics. Today, I would like to share my story about memory, what's eating my RAM. So from title, I guess you already have an idea of what problem I'm facing. Basically, the memory usage of my service keeps going up, and I don't think it's normal. To be more accurate, my service is a long-running and stateless service. It takes a request, process it, and send back the response, and no state left in the service. However, the memory usage keeps going up with more and more requests. I'm not an expert in this domain. I hope that after listening to my story, if you don't have any experience dealing with the memory problems, you could have an idea of what kind of a problem it may be and how to analyze it. And if you are an expert, I would be very happy to hear any advice and ideas. Let's get started. Here is my story. It started with an alarm saying memory usage is 90%. So my first question was, okay, what's this alarm and why it's important? And after that, I went back to the basics because I need more details about how memory allocation happening in C++. And finally, I tried some tools and discovered some problems, memory leak, and fragmentation. So the alarm, we released some new features, all test green, and we are happy. We deployed to the beta. And after a few hours, we got this alarm, 90% memory usage. So in Bloomberg, we have different levels of alarm, and that one is the top urgent one. So my first question was, why is that important? What if I do nothing? I made my research, and here are the consequences. So first, we will have more and more swap, which means the operating system needs to do more and more effort to move inactive data from RAM to disk to make more space in RAM, which will slow down the whole system. And secondly, operating system will not allow one process to take all the memory. So for example, in Linux, Linux has this out-of-memory killer. Your instance will be killed if it uses too much memory, which means service disruption. And that's terrible. Imagine your client is doing an intraday pricing for his portfolio and the service is not responding. It's something we don't want. Finally, we are in a multi-tenant environment. So processes are sharing the same resource, which means the impact is not only limited to your service, it could slow down other critical services, which may be very sensitive to the delay. So, okay, it's important. Let's now find out what's happening and what's eating my RAM. So the first thing we can do is find out, okay, which process could be a candidate. So I log on to the machine using top to find the top consumers, and those are the candidates to have a further check. Then the thing is that what really help is a dashboard because having only the current memory usage is not enough. With the metric and dashboard, we can check the memory usage over time for a given process. For example, you can see in my case, this application's memory usage keeps going up, and that's the problem. And as I said, like my service is stateless, no state left after processing one request. So given that the traffic is stable, which means I don't have more traffic from yesterday to today, and I don't have exotic requests. So it must be something in the code make that memory usage going up. So the problem comes from the code change, but how could my code impact the memory usage? What happens between like this live code to the memory usage? So I went to basics to understand what's happening. From my C++ code to RAM usage is a long way, but most of the works are done by two things. One is malloc, and another is the operating system. So first, we don't need to deal with the hardwares. The operating system will map devices to the virtual memory, so we don't need to care about where my data is. Is it on disk or is it on the RAM? In the application's point of view, it's just a virtual space to use. Then malloc will use the virtual space for different purpose. It will use some space for stack, for heap, for data, for text, for kernel. So the memory usage of my process should be basically the sum of those blocks. And I know kernel data text is small and static. And stock size is limited. Usually it's like 10 megabytes in Linux. That's why we have Stack Overflow, the growing part. So the growing part must be heap. Let's check what's happening in the heap. So if we look inside the malloc, this is a basic malloc memory map, and I take the example of glibcc implementation. The definition of a heap is that a contiguous region of a memory subdivided to chunks. And a chunk is the basic unit of allocation. So when you call malloc, you will allocate a chunk. Then for multi-threading, we should allow multi-active memory regions. So the arena is for that. It's not a memory region, but just a structure which has the pointers pointing to the heaps that belongs to that arena. So main thread will use the main arena, which point to the main heap. And for other threads, we are going to use other arenas and which can have one or more heaps. The difference is that those heaps will be allocated in somewhere else in the virtual space by mmap, not the main heap. So here we have two system calls, mmap and break. So BRK is for extending the main heap, and mmap is to allocate a large region of memory directly from the OS. So these arenas will use those mmapped base heap, and the main arena will use the BRK based heap, which is the main heap. And when we call those two functions, memory usage goes up from OS point of view. So what is inside the chunk? So chunk can be allocated to an in-used chunk. It looks like this. We have the payload for data, and that's the address malloc returns to your code. And we have the metadata like size, prev size, information about the arena, if it's from mmap function, if the previous one is in use, etc. So a chunk can also be freed. And the only difference for freed chunk is more metadata. So we have back and forward pointers and sizes. And a chunk can be also combined with adjacent free chunk to a larger free chunk. So you may notice that I put this word mark as free here. What happens when we free a chunk? So it's actually just marked as free. So from the OS point of view, this free chunk still belongs to the application. That's why most of the dashboards of like C++ applications, the memory usage always goes up or keep flat. Sometimes it goes down, but not due to a free. And malloc manages these free chunks in bins to reuse them. Bins are basically a mutex plus linked list or double linked list. Um, Based on the chunk size, we have different bins, unsorted, small bins, large bins. In the example of glibc implementation, we have many small bins and a few large bins, and that's for reusing those free chunks efficiently. Okay, so now we have everything ready. Let's take a look what's happening when we allocate and free. So there is a heap. We have 2 in used and 2 free chunks in the bin. And when you allocate a chunk, if the appropriate bin has a chunk in it, we just use that chunk. And when we free that one, we will place it back to the bin, to the appropriate bin. And if the chunk is adjacent to another free chunk, we're going to combine them to a larger chunk. And if no chunk is available, that's the moment we're going to create a new chunk on top of the heap using sbreak. And this means the heap is extended and the memory usage is rising. And if the request is large enough, so there's a mmap threshold, and malloc will call mmap to request memory directly from OS. And this is another moment the memory usage goes up. So, however, when this chunk is freed, we are going to return it back to OS. We are going to call unmap. And that's the moment memory usage curve goes down. So that's a simplified version how malloc works. There are still a lot of mechanisms like tcache, topmost. All those efforts are for reusing the free chunks efficiently. So seems like OS is smart. It's doing swap, moving inactive memory from RAM to disk. Malloc is smart, manage and recycling free chunks holding by the program. So what could be a problem in my application? I'm going to talk about 2 main problems like memory leak and memory fragmentation and how to analyze them. So firstly, memory leak. The memory usage looks like this. The application keeps allocating memory from OS. And the definition of memory leak is that memory which is no longer needed is not released. So the first example will be new and forget. So it's why we prefer modern C++ and RAII, since no object leaks, no resource leaks. And the second example is that, okay, even I'm using modern C++ container, I can still leak by keeping data which no longer needed. For example, I have an in-memory cache, a map, and I keep adding entries but no evictions. Eventually, those spaces will be released when the application exits that container destroyed. But it's still leaking because we are keeping those datas no longer needed. Then a mistake is missing virtual-based destructor. When your object get destroyed, the base class resource will be leaked. The last example is the circular dependency. Imagine we are using share pointer everywhere in our code. This share pointer, it becomes a garbage collector based on the reference counting. And a classic problem for reference counting is circular dependency. So no one let go and we got memory leak. Those are the types I discovered. Feel free to send me a message if you have other examples that would be interesting. So, okay, that's the memory leak problem. Do I have it? Do I have it in my application? How can I detect it? So I discovered some tools. I firstly found this test allocator tool. So allocator handles all the requests of allocation and deallocation of a memory for a given container. A little bit of history about allocator is that in the very early discussion about standard, people agreed that containers should be independent from memory model, um, but limited to the language, we couldn't have it. So STL containers interfaces had to be rewritten to accept allocators. So after that, in 98, we have stateless allocators. And later people think, okay, um, allocators can have state. And even better in 70, we have the flexibility at runtime with PMR. So back to the test allocator, how to use it. So if you check the container template, for example, the vector, there are two parameters, type and allocator. So you can inject any allocator to this vector, which means you have the control on how the vector is going to allocate memory by using different allocators. This test allocator is a Bloomberg implementation. The idea is just this allocator is like a wrapper of the standard allocator. It will record all the allocations and freeze. So, and try to match them. And if there's any mismatch, that means there's an issue, a memory leak or invalid free. So the advantages are it's fast, it's small overhead, and it's scoped. For example, if you already have an idea where the leak could be, you can inject this test allocator only to that scope, and you don't need to care about other parts of the application. The disadvantage is okay, you need to change your code and you need to compile link. So I don't have any idea where the could be in my case, and I don't want to change the code. Do we have something easier to use? Then I found address sanitizer. Basically, it's a compiler instrumentation module plus a runtime malloc library to replace the default one. So it can do some record, very similar idea than to match the allocations with deallocations to find out the leaks. So this time, the advantage is that you don't need to change the code. You just need to compile with the option. And other advantages is it's fast, like 50 to 100% slower, but it's still fast compared to other heavy tools. However, the disadvantages are like compile and link required and also extra memory cost. Well, in my case, memory usage and slowing down are not a concerns because I'm doing it in beta environment. However, I would like to do the profiling immediately without waiting for a new deployment with the address sanitizer. So then I found this Valground toolset. So Valground is a set of tooling including memcheck, massive, dhat, etc. Memcheck is a memory error detector, and massive is a heap profiler. And this time, I don't need to do anything with my application. I can just run the application under background command, and background will run this application in a sandbox and insert its own instructions for profiling and give me the results. So the advantage is that no code change required, no compile link required. However, the disadvantage is it's slow. It's very slow, 10 to 30 times slower, and extra memory cost is heavy. Here you can see the three tools are trying to catch the problem from different places for the test locator is trying to catch from the C++ code. Address sanitizer is more malloc library, and background is just above the operating system. So they are all useful tools. The results are different, and we can put them into two groups. So the first three are similar. They are one snapshot in the end. So the results of the first three tools are a leak summary with all the leaked size numbers and call stacks. So with that, there's one problem in my case. I have a lot of external legacy libraries. They are introducing a lot of static leaks. So when I say static, I mean they take 3 megabytes when the service starts and hold the 3 megabytes until the end. Um, it's not leaking more and more memory with more and more requests. They are not the real issue I'm looking for. So what I'm looking for are those leaks growing with the request numbers. But now, like if we have this summary, we have thousands of call stacks on one snapshot, and it's very hard to tell which one is the growing one. So that's why massive is helpful. It's snapshots over time. With the visualizer, you can easily find out, okay, which stack is using more and more memory. And now we have the call stack. We can trace the object, find out who should release and when it should be released and why it's not released. Then the memory leak is fixed. Something I learned from memory profiling, some tips like static leaks can hide the real issue, so we need enough traffic for profiling to trigger that memory leak. They are all good tools, but for different cases. For example, if you have a good idea which part of a code could make the leak, you can just use test allocator, which is light and easy. And catch the problem in earlier stages. For example, you can integrate address sanitizer in CI. However, sometimes you don't have good test coverage to trigger the memory leak, so you need to catch them in a later stage. That's why it's better to install the tools so you can start the profiling easily. And as developers, care about the life cycle and the ownership. Like you should have a good idea who is owning what and when they should be released. So memory leak is now fixed. The alarm stopped, but my service is still using a lot of memory, which I don't think it's very logic because there's no state. The business logic is quite straightforward. So what else? Well, I would say maybe it's fragmentation. So fragmentation is the case in which you have free spaces, but you cannot reuse them for new allocations. It could be the case like, okay, you all play Tetris, right? So blocks are not placed correctly. So we are wasting spaces between them. Or it could be like this car parking on the right side. One car is taking two places, and we are also wasting spaces. So that's two types of fragmentations. External fragmentation like the Tetris, I have free space, but I cannot find a free chunk for the size required by the new allocation. For example, I allocate something, then I freed something. Now I need to allocate one more chunk for a size of a 4, for example. I cannot find any free chunk with that size, so I need to extend the heap which means memory usage goes up. And another type is the internal fragmentation. It's like this car. We allocate a large chunk, but we only use a small size of it. For example, I need 2, but every time I will allocate 8. That's wasting space internally. And do I have those problems in my application? Um, you may remark that I'm using the word estimate. So how to estimate a fragmentation. So unlike um, memory leak, you can tell there is or there isn't. So the question for fragmentation is more how bad are we? So how can we estimate it? I learned these formulas for estimations, which makes sense to me, and I would like to share to you. For external fragmentation, the formula uses the largest allocatable block divided by the total free memory. For example, if most of the allocations can be done with the free chunks in the bins, and your free space is small, and the largest free chunk is large, and that value is close to 0, which means there's no fragmentation or not badly fragmented. However, if your application is holding, for example, 1 MB free space, but they are badly fragmented, and the largest free chunk is only 1 KB, and that means um, new allocation requiring more than 1 KB will need to be allocated in a new chunk, and the memory usage is rising. And in that case, the value is close to 1, which means very badly fragmented. And for internal fragmentation, is something like, okay, we should avoid useless or underused allocation. The formula is using accessed size divided by total allocated size, which means the efficiency of this allocation. For example, you allocate 1 MB and only use 1K. It's wasting because you don't need that much. If you only allocate 1 KB and you access all of them, and there's no fragmentation, and the allocation is efficient, the value is close to 0. You might find some for other formulas to make the estimations, but those tools are straightforward and for me it's easy to understand. So now, how to get those numbers? So for external fragmentation, I found this malloc it's useful. It's a C function which provides information like total size, in used, free, which allows us to do the estimation. In my case, you can see my application is holding 240 MB in total, and 210 MB and 10 MB are free chunks. However, the largest allocatable is only 63 KB, which means any allocation required more than that will push the memory usage up. So the result is very close to 1. Okay, so it's badly fragmented, but how bad are we? I need some benchmark, so I take another service here. Service B has very similar traffic and business logic as service A. However, you can see in the service A, well, the in-use memory is very similar to the service B. It's 30 MB something. That's the business logic who's holding those memory. However, the total memory and you can see the free memory of the service B is quite small. It's only 2 MB comparing to 100 MB in service A. And Well, the result is still close to 1, but it's 0.95. Is much better. And a more visible comparison is that, okay, if I can leave the services run, the service A for 1 day, it will take 400 megabytes and it's still growing up. And for service B, I left it run for 7 days and it only takes 200 megabytes. This is not a very accurate uh, result. It's just for estimation. It will give you some idea how bad the fragmentation we have in our service. And for internal fragmentation, I allocate something in the memory. I need to know how efficient this allocation is. So I need to know the total allocated size and also how many bytes are accessed by the application. The tool in background sets, we have this D hat. So it can help with this. The tool provides a summary of the allocation blocks and the usage data. For example, in the core stack on the left, allocated 1.5 gigabytes in total. However, they never read them or write them. So the result is 1, is 0 access blocks. And the example on the right, it's write a little and it has even fewer reads, which shows the memory allocation is underused. So the formula result will be close to 1 and says we are wasting spaces internally. So after knowing what is fragmentation and how to estimate them, what can we do? How to reduce the fragmentation? There's no magic, like people are doing a lot of efforts and there are some examples. Mesh is a technology doing automatically compact. If you have two physical pages and they are both fragmented, and there will be a good chance that you can mash them into one, move all the like the yellow data to the other one, and release one page. So if you're interested, please check this CppCon talk. It's very interesting. And on operating system layer, body system is a technique used by Linux for allocation with a size of a factor 2 to reduce the external fragmentation. And on malloc layer, malloc implementation usually have tunable parameters. You can limit the number of arena, malloc returning memory to OS more frequently, but there's always a trade-off between memory usage and performance. And gmalloc is another malloc implementation, and one of the features is to reduce the memory fragmentation. They're using different data structures to make a better reuse of the freed chunks. So you can see they are trying to reduce the fragmentations in different layers. And if we think about the source of the fragmentation, it's the memory usage pattern of our code. So it's different if you do allocate, deallocate, allocate, deallocate, or you do allocate, 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 deallocate, deallocate, deallocate. So if we think that's the source of the fragmentation, efforts in malloc and OS, they're easy to use. They are generic solutions, but it's hard for them to predict memory usage patterns in our application. But we as coder, we know better our code, we know the workflow, and we have a better idea on the memory usage pattern. So can we do something? Maybe efforts in the code is more efficient to reduce the fragmentation. Then I found this CppCon talk by John Lakos about memory locality. In his talk, he focused on the performance, like how local allocators speed up the memory access by improving the memory locality. However, I think it could reduce the fragmentation as well. Here is what I understood about the memory locality. Let's take an example of, so I have long-running stateless system. And long running means it starts and run for a long time, and stateless means I receive a request and process them and no state left in my system. And the system, for example, it can be broken down to 4 subsystems. We have some code for log, we have some code for decode, uncode of the request, we have the TCP connection, and we also have the code for process the request, which is the business logic. And they have different memory allocation patterns. For example, the log and the TCP connection are both allocating memory and holding them for a long time, so long-living allocations. However, decoder and process requests, those subsystems will allocate and free them after a request is processed, so short-lived allocations. And if all the subsystems are allocating the memories in the same space, it will be something like this. So for example, when we start to process the first request, different subsystems are going to allocate some memory with different colors, and they are mixed in the same space. And when the first request got processed and all the short life cycle memory allocations are freed, what's left are the memory blocks by the long-living subsystem, and the fragmentation happened. So the idea of a locality tells us we can use local allocators for those different subsystems. For example, if I use local allocator 1 for short-running subsystem and local allocator 2 for long-running subsystem, and that's how it goes. The same request comes, we do the same memory allocations, but in separated spaces for different subsystems. And when the first request got processed, we free all the short-living subsystem holding memory, and we don't have fragmentations. If we compare the memory layouts in 2 cases, using local allocators could reduce the fragmentation. In theory, it's a very good talk about memory locality with a very good benchmark to show like how local allocators improve both physical locality and temporal locality, and how that improves the performance. And I do believe better locality could also help to reduce the fragmentations. So I made this a small experiment. So my execution has 2 subsystems, long and short, and in the loop, the 2 subsystems are allocating memories, and the short system will release memory after processing 1 request. And we run this code with global allocator and local allocator. Here is the result. It's the same business logic, and in the end, they both hold the same amount of memory, which is the total in-use memory. It's around 8 kilobytes. However, the total allocated memory are quite different. So the one with global allocator is using 89 megabytes, and the one using local allocators only use like 100 and 30 kilobytes. So the global one, it has 2 million free chunks, and the largest one is only 48 bytes. And if you say the fragmentation results, the global one is near to 1, and the one with local allocator, we are quite good where we're not fragmented. And also, in terms of timing, the one with global allocator will take more time than the one with local allocator. So if you are interested, there are some additional readings and tech talks for more details. For my story, we do have memory leak. We fixed them. We do have fragmentation problem. We're still trying to reduce it with different solutions. gmalloc gave us very good results. However, the concern is that when we start to relying on gmalloc and we don't pay attention to our code, it's dangerous. If one day we need to stop using gmalloc for some reason, it's very hard to get back to the glibsys malloc. Local allocator should be more efficient solution. However, it requires our code to be compatible with the memory allocators. And also we need to be very clear about what we are using. Otherwise, we may have a worse result than the standard global allocator. So hope you enjoy this talk. Next time, if you memory problems, please come down and profile the memory usage. Thank you for your time. Please leave comments and questions in the Discord channel. And thank you and enjoy the conference.